at 1200, then every 100 degrees it gets a cut. So this is just happen to be, you know, for this curve, you happen to end up with like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 35 to 40 components. Okay, is that clear? That's how it cuts it up into those NBPs. And if you look at the first one, this line here, that's about 111 degrees Fahrenheit. So that's your NBP 11. So that describes this component here. Okay. And it's probably mainly C6s and C7s or something. Back here. All right. So that's the default set. And then I made this little graph here. It's important to look at how it cuts it up, because if you want to make a really good separation between, say, this light product and this heavy product, and you only have one cut to play with, it's either going to stick all this into the light product or into the heavy product. So you may want to ask for more than the default number of cuts in this region, so that you can do a better separation. So let's say I asked for 6 here. So 3 would come here maybe, or 4 would come here, and 2 would come here. So it has more leeway to make the products that you want. So if you just ask for one cut, you know, it's either going to end up here or end up here. It's not very accurate. And the default cuts, the 28, 8, and 4, that's originally designed for partitioning crude oils. So materials that boil below the first cut is combined with the first cut. If you look at the plot again, right here, see, this is a material that boiled, well, this is the light ends. I shouldn't use that one. Like this one right here, you have stuff left over. Well, this is actually an average of this curve. It actually does some sort of integration. But if you do have a lot left over here, after it makes that cut, it will just combine it, and you'll just get a big last cut there. You know, it has a higher volume, higher flow rate. And again, if you put in the average gravity or a curve, if you gave it that, it'll calculate the number of moles in each of those cuts and the volume. Okay. So as I mentioned, usually light ends are like C5s and up, and hexane is like the upper limit. I mean, you may see C6s, but anything lighter should be considered individually, you know how much IC4s, NC4s, and propanes and up. Now, if you do provide light ends, it will match it to the curve, and it will adjust the rates up and down. It will take the composition, and then it'll adjust the rates up and down so that your the highest point of the boiling point of the highest boiling light end will intersect the TBP curve. Okay. And then anything below that will get thrown out. And let me show you what I mean by that. So if I had, like if my this is the light ends. So if I had cuts down here that are just based on my TBP curve given here, it'll get thrown out because it'll actually look at my light ends data and then extend it down and throw out all these cuts, because it wants to look at your individual composition of the light ends. Oops, why did it go away? Right here. Oh, because I have this up, sorry. So does everyone understand that? Like it will actually throw out any cuts down here because your light ends data is more important. Okay. Right. So you can say, I want my light ends to be a fraction of the stream, or you could give it individual flow rates of, like, I have X number of X moles of methane, X moles of, pentane, and then if it doesn't add up to 1 or 100 or the rate that you gave it, it will normalize it for you. Now it has everything in terms of the normal boiling point, specific gravity, and the molecular weight. It will go ahead and calculate the other properties it needs. So normal boiling point, as I said, it integrates across the cut range. So you'll see that if you just kind of eyeball it a bit, like if you take this little portion here, this boiling point is about halfway. So it's, if you were to integrate that, for small cut points, that's usually like the average. It's like usually the halfway point. Okay, and that's what the other option is. There's two options to do that in Pro 2, and the default is this one. Then the other one is just take the midpoint, the temperature midpoint. So for small cut ranges, these two almost become identical. And let me show you that. You would choose it in the, let me close this curve because that's in front and it won't let me do anything without it. It's in the assay processing window. The assay processing window is under this icon here that looks like a miniature of that picture you just saw. Looks like little steps. And here's the characterization options. And remember we were talking about the curve fitting, the cubic spline, quadratic, and the probability density function. You can choose whichever one that fits your curve better. Use the conversion. This is to convert between D86 to TBP or D1160 to TBP. And I was going to show, here it is. Here's the two methods for calculating the normal boiling point. So it'll take the liquid volume average or the temperature midpoint. So those are the two. Okay, so if you were to enter a gravity curve like an API or a specific gravity versus volume percent, Pro 2 will calculate the average gravity for each cut. And then if you just enter average gravity for the entire stream, it'll use the Watson K, this equation here. Remember, there's a cube root over the specific gravity. So because K is relatively constant over the whole range of your crude oil, it's a pretty good assumption. So it'll hold this number constant, and then you have the specific gravity. So it'll calculate the boiling point. Is that the way? Enter the gravity, uses it. Yeah. Oh, okay. Now you know the gravity, and you have the Watson K. It gets held constant, then it could calculate the other number. Okay. And then when molecular is calculated, again, that correlation is pretty weak. So if you have data for molecular weight, go ahead and enter it. Then from these three properties, you can calculate like critical properties, enthalpies from knowing these three. Okay. Now, I mentioned that it's important to ask for many cuts when you have overlapping areas in your assay, and that's in the modified primary set here. If you look at this, remember that 100 to 800, it makes 28 cuts, which means every 25 degrees it makes a cut, and so on, every 50 here and every 100 here. You can modify it by just changing, adding more to this, or you can make your own cut point set and say, you know what, give me like 40 cuts here. And the thing you're sacrificing is just calculation time. The more cuts you have means the more components it has to carry throughout your whole simulation. So you kind of have to balance that. You don't want to have too many components, but you want to get enough in the overlapping areas so you have a good separation. Okay. In that screen, you could actually change it just like I did. I asked for 40 cuts. You can have a secondary cut point set. Means which it just means that you don't want to use, you want to use a different set for a different stream. Like if you have very light feed and very heavy feed, and you don't want them to get blended together into one whole set, you would want to use a separate set. So you will actually end up with, say, like 100 components instead of 40. You know, you'll have like 40 each and then a little bit of light ends. So you can use more than one set. Then for the output, as I showed you, it actually will boil the components out to give you the D86, the TVPs, etc. And 1% and 98 liquid volume percent are arbitrarily defined as the initial boiling point and end point. So when you do want to make specifications, like you want your kerosene end point to be a certain number, you should use the 95 liquid volume percent. And then if you want initial boiling point, you should use the 5%, because these are just arbitrary. And you saw how, you know, the curve fitting, sometimes it just linearly extrapolates it, or it'll do something funny to get to the end point and the initial boiling point. So it's more reliable if you use the 5% and the 95% for your specs. Okay, so this is just some summations of how Pro 2 creates one set from all your assay streams. If you have more than one assay, for example, we just looked at one, right? We had crude, but if you had other assays, sometimes refineries, instead of just providing the feed, they actually will just do assays on the products and then blend them all together for the feed. It's more accurate that way, because so they know that they're actually going to get those products. So if you do that, this is how Pro 2 will blend them all together to make one set of components. It just takes the sum of, you know, it takes each individual boiling point and multiply by how much of that species is there, and then it'll give you the boiling point for the cut. And here's an example of how it does that. It's called blending. It's blending more than one assay together to create one set of pseudo components. For example, if you look at this feed, here's a little TVP for it, and this is for feed 2, this is for feed 3, and you have about 150, say, barrels, and here's 400, and here's 100. Now, if you were to look at this temperature range, this 10-degree range here, the boiling point for that is 212, and for this is 211. So you kind of go in the middle here, in the middle here, and the middle here. And this is 213, and then it has its own specific gravity, sulfur weight percent. Now, after you blend it, you'll see the component that you're going to use to represent these three feeds will have a normal boiling point of 211.5 and specific gravity of this and the sulfur weight percent. And if you look at that, you'll see it's more biased towards this cut here, because you have more of this flow rate. You have more of this stream going into the mixing. So because of remember the slide I showed you, the summation? Because of these equations, the more you have of something, that one is going to be going to have a bit better representation in the blend. Okay. Any? Oh, this is rate like for the whole stream, and this is, say, the rate of the cut of just that area that's in the shaded area. Yeah. Okay. How's everyone doing? Should we take a break and then come back at 4:30? Yeah. Okay. Let's take a break.